by having a look at by having a look at different kinds of variables. And let's go back to these slides that we had. Hold on a second. So thing here. So, yes, so that should be it. That looked like work, right? So these are the slides that where we stopped last time. An algorithm, a machine learning algorithm, we have input data, and we also have some output data, and all that has to be mapped to our surrounding and to our phenomena that we are looking at. And there are some types of data that play a role in data analytics. And for us, it was important to see the categorical, how to get from categorical data to numerical data, because our computer only can digest some numerical data. And if we look, for example, at a classification problem, we say, well, the output is our output variable y, and it has two realizations, and we can do that with, we can map here from categorical data to numerical data by saying y is -1 for the one class, and it's +1 for the other class, for example. We'll have a look at that later on. If we have more categories that we want to map into numerical data, one approach is the so-called one-hot encoding, where we say, okay, so we take a vector that has the length, the same length than the number of categories that we have, or the number of classes that we have, we order all possible outcomes arbitrarily from 1 to the number of outcomes, and we say that xi is, so the ith component is 1 if the data value is the ith outcome of 0 and 0 else. So that was one thing, this one-hot encoding, and the other part was another idea that has some advantages was if we assign to each category a random vector in some fixed dimension. So that could also be possible, right? Just randomly choose a vector in a dimension that is large enough and assign to each class this vector. These are two things, and what we want to have, where we stopped last time, was seeing how can we do that if our phenomena that we want to describe is actually given by some text. And if we want to do some text analysis, we have to map our text into numerical data, or design a random variable that somehow describes our text. That's the idea. So you know, I mean, what can we do here? I mean, what would be your ideas in transferring a text, right? Something in written form, like these slides, for example, into a numerical variable, into a random variable. So, for example, I mean, I could take a picture of the text and feed it into our algorithm as an image. What do you think about that? Is that a good idea, or is it not so a good idea? Umer, what are you thinking about that? Is it a good idea, taking a picture of a text and then take the grayscale values of this text? I cannot hear you. I cannot hear you. Is it?
And now can you hear me?
Yes, now I can hear you.
Okay. So my mic was muted. So I was saying that it's a bad idea, but there are some funny research papers which argued the other way around, and they also had some nice results. But in general, it's a bad idea.
Yeah. Yes. So I also think it's not the best idea that one could have.
Yes.
I mean, why is that so? Because, for example, if you turn if you turn the sheet of paper and you take a picture from another angle, you have a complete different input vector x, although it describes the same phenomena, for example, that you want to model in your data, right? So, so there are perhaps some other ideas, and we want to go through these ideas a little bit so that you can also use it into your assignments. And the idea is, if you want to say we want to go from text to numerical data, and we say, okay, so how could that be possible? So we have one text here, and the text consists of words, word 1, word 2, word 3, and so on, and word 17, and then there is word 2 coming again, and then, I mean, this is how text looks like, and you have your word 5 perhaps here in that thing, and the concatenation of words, right, that is described by a text. And what you could do is, you could say, well, I choose all the words that occur in all the texts that I want to analyze. So all the words, and I take them and I name them, and I design what is also called a dictionary. So the dictionary consists of all words that occur in all the texts that I want to feed, for example, into my classifier. Okay, so that means I have a word, I have a vector, I have a word 1 up to my word, I don't know, 3,750. I mean, there are lots of words typically in the text that we have until our word n. Okay, and what I could do now is I could assign to each document, so to each text that I want to analyze document, I say, well, I just count the numbers. How often does word 1 occur in this text? Right, so the number of word I in document I. Right, get a little bit the point? So that means if I have a very short document that only has 5 words, most of these vectors are 0, and then the word, the 4th word in my dictionary that I have already is occurring like 2 times, and anywhere else are 0s, and there is another word occurring here for 1 time. But this could be done. Umer, what are you doing there? You have some cable hanging around.
This is the cable of the monitor.
So this is something one could do in the first shot, right? Counting the number of words, giving them an order, and then say, okay, so now I can differentiate different text documents. So document 1 looks like this. Document 2 has other words in another frequency, and so on and so forth. Now, fine and fair enough. What you want to do further is, if you want to model such texts, you have probably the disadvantage that there are lots of words that occur frequently in many documents. For example, words like and, so, or great. In some texts, you hear very often the word great, and so on and so forth. So very, very often you have words that occur very often in a lot of documents, right? So, for example, if you want to compare these documents, 3 documents, 1, 2, and 3, and then you have the word a or and it occurs here, I don't know, 10 times and 20 times and 30 times. Whereas words like, if you want to do some, it depends on the example that you have. For example, if you want to discriminate between spam mails and non-spam mails, you might have some words that if they occur very often, they are very discriminative for this document. For example, Prince and Africa, or Russian girl,
Congratulations.
or I mean, we all know these kinds of spam mails, and if these words occur like rather often, right, so 3 times here and 0 times here and 0 times here, we actually, right, we don't want to have this. We don't want to have this common word taking over the whole weight of this vector. Okay, so you want to have a kind of normalization that somehow allows to find out words that are somehow special. Right? We want to discriminate between words that occur in all documents and words that occur only rarely in a few documents that might have some discriminative character. Okay, so what you do is you normalize in an appropriate way, and this is done. This is done here in the following way. So let's look at this example here. So you have 2 documents and you have like 2 texts. Okay, so the quick brown fox jumped over the lazy dog's back, and document 2 is now is the time for all good men to come to the aid of their party. So this is just 2 random texts,
So okay, but I have one question here. So can't we just remove all these words which are very common words from the list of words?
Yes, we could do that, but it's better. We could do that, and actually, that's what we want. That's what we're doing here somehow, because we will find a normalization that if the words occur frequently in all documents, their weight tends to 0, and then you can just and then you can just wipe it out.
Okay.
But so yeah, but you can do it. In order to do that, you have to know them, and this is how you automatically get them.
Yeah. Okay, that's good.
Right? So so here the document 1. If you look here, document 1. Why isn't that red? It should be red. For document 1, you would have this input vector. That would be the map here from the phenomena to your input data, and document 2 would look like this, for example. Now, if in order to, so you have P, P is the number of different words that we have, so the length of the dictionary, and this is also our input dimension, because it depends on the length of the dictionary. And the ith entry is the frequency of the ith word in the document. That's what we just said. So how often does one word occur in the ith document? And what we want to do is we want to normalize these vectors so that the length of this vector is not somehow biased by the length of the text. This is what you typically do here. So you normalize here with this with the L1 norm of the text, and so the L1 norm of X is the sum of the Xi. Right, if you forgot that. So the first vector would be normalized by 1, 2, 3, 4, 5, 6, 7, 8. So it's 1/8 times this, and the second document would be normalized by 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 1/9 of this vector, just to get the bias out there of the length of the text. But still, as I said, this does not solve the problem of common words that occur. And what you do here is you look at the so-called term frequency and inverse document frequency, TF-IDF approach, and the idea is that words have to be frequent and distinctive to get some weight in this vector. So that's a frequent and distinctive to get weight. For example, words like Russian girl and so on, if in a spam mail, or win and lottery and so on and so forth, they should have more weight in this vector than common ways like good day, sir, and so on. So we can do that by normalizing that if n is the total number of documents that we have, and this dfi is the number of the documents containing this word I. We have tfij is the number of occurrences of the word I in the document j. Then we weight it, and the ith entry of the document vector I is just given by, so this multiplies it. How often does the term occur in the document? That's the usual thing. And here we have a log term that goes to 0 if dfi goes to n. So if the number of documents where the word occurs, if I have the word prints in all documents that I want to analyze, it will be n divided by n. This is 1, so there will be log of 1 at 0, so there will be a 0 entry. And this is what you mean, Umer, if you say, well, can we just get rid of these words? If there is a word that occurs in every document, it will automatically have the weight 0. Okay. And then, I mean, so in practice, if you generate this input data matrix X, and you see that there is a row that only consists of zeros, I mean, you can just ignore it.
Yeah.
Okay. And after that, again, in order to not to take the length of this document, in order not to take the length of the document into account, we normalize again with this L1 norm here. Right. So you can use that in practice. I mean, we have some tasks, right, in the tutorial.
Yeah, we have them.
Yeah. And then you can find that out and see how you can choose your data as your text as an input here. There are other approaches that are a little bit, more, let's say more subtle, because what you don't do here is a text document that has exactly the same amount of words and the same number of words. If you randomly permute them, you will get the same representation vector. You will have the same input vector if you do this approach. And sometimes this is probably not the best thing, because sometimes, in particular, if your text documents are very short, you can have complete different meaning of the text with the same words. So what you can do here is you can go to so-called n-grams, which means that instead of word 1 and word 2 and word 3, and word 4, you take a set of words in a given order. Right? So you would have, I mean, and of course, so you would not have a dictionary consisting of word 1. You would have dictionaries consisting of 3 words in a row in a given order. And of course, this gives you a better way of distinguishing between documents, but it will also blow up some of the size of your dictionary. Because you would, instead of having like 1, 2, 3 entries here, you would have 1, 2, 3, 4, 5, 6 entries there if you do that. Because any different order is a different word. Yeah. So depending on the size of your training data, you can see how large you can use this n-gram. Umer, you want to say something?
Yeah, so I was saying that, is this everything clear to the students? Because n-grams, maybe we can do a little bit yes or no.
Yeah. Well, yes, vote. I don't see the vote.
So the question is, does everybody understood the n-gram, word n-grams? Can you do an example? Daniel said.
Yeah. Okay, so an example. So if we go to this, text here, okay. So in n-gram, you would. So this is the dictionary if we take word by word. Okay. The does not even occur here, but anyway. If we want to go for a 2 gram here, for example, we would have the first entry would be the quick. The second entry would be quick brown. The third entry would be brown fox. Fourth entry would be fox jumped. You know what I mean? And then you would assign to each text the vector and would count how often do these 2 grams occur in that text. Right? Then you have then you distinguish between orders of 2 subsequent words. Is that?
Yeah. So I mean, in short, normally we had in terms of term frequency we had 1 gram, and now we have a 2 gram. And if we group more words together, then we have a 3 gram or 4 gram.
And the more words we group together, the longer will be our representation vector.
Yeah.
Right?
Okay, then let's go ahead. Yeah.
Okay, so then, yeah, I mean, if you play around with that, you will see very quickly how good that is and what you would need. So this is not very demanding from an intellectual point of view, I think. Yes, so what is better are kind of approaches like word-to-vec approaches. And these word-to-vec approaches, you can have a look at that. They are, I mean, how they work is they assign, roughly speaking, they take each word as a categorical variable that you have, and they assign to each word a random vector and use that as an input, and then they train a deep network to get some representation for this vector. So this is the rough idea. Interesting work, and also some of the state of the art of how you represent texts at the moment. Yeah. But I mean, for playing around and for doing some example and to get to some point, this bag of word approach is quite good. It was state of the art for a long time. This TF-EDF approach until machine learning has come. So yes, so you should be prepared to digest some text and to do some experiments with it. And then I would like to go to a more or a better, or our first binary classification task that really that would really help you also in practice. And this is logistic regression. So this is this thing here. Okay. There you go. All right, I see. Okay, good. So binary classification and logistic regression. We have, okay. We started last time and at the very first lecture with this binary classification problem where we say, okay, we have input or labels that are realizations of random variables. X is a high dimensional vector in RP, and Y is our output vector. And if we want to do binary classification, we have modeled our output, right? I mean, it's a categorical variable in practice, and we say it's -1 if it's class 1 and +1 if it's the other class. We have this joint probability density function of our input vector X and Y. And we said that this was an example here. I don't want to go so much into the details. You can look it up. we've done last time. And we wanted to find a suitable decision function f that assigns a plausible output to our new input. And the ingredients that we needed to that were the non-negative real value measure for the deviation of the output and the decision function, which we call the loss function. And we said that if we have this expected loss, and we find a function that minimizes here our expected loss, we say, well, this is our decision function. And examples there are the squared loss and others. So if we, and this global method where we predefine a class of functions that is described by finitely many parameters, for example, affine functions here, and we said that our best decision function is the one that minimizes the expectation value, right? Remember, we don't know this expectation value in practice, so we have to estimate it via our training data and our distribution. So we take this average here, and we say, okay, so let's take the average and let's find the theta that minimizes this function. And that was our approach. Now, that was our approach. Now, for a binary classification problem that we had, okay, there was a mistake in how the slide set up. But anyway, so we have the input labels and realizations as given. The task was then to find a suitable decision function f, where we want to decide y is -1 if our decision function is negative, and y is +1 if our decision function is non-negative. And we said, well, there is, for example, this squared loss that we can use. But there are probably other losses, and one loss that is actually a very natural way of measuring, if you want to do a binary classification, is the 0-1 loss. You just want to count the number of misclassifications that you're doing. Right? So you have, I don't know, 20 samples, and then you count how much do I decide on these 20 samples, and you count the number of misclassifications. And that, of course, is also a very valid loss function. And this loss function looks like this. It's called the 0-1 loss. We say, well, our output y, we compare the signs of our decision function of the output function, and the signs are equal if the product here is positive. So if the product is positive, we have no penalty, right? That's good. If f of x tells us greater than 0, but the actual y that corresponds to it is actually negative, we get a penalty on that. And this is if the product of the outcome and your decision function is negative. So you have this loss function 0-1 that counts actually the number of misclassifications. Okay, is that? I have the feeling I'm too quick. No, is that fine? I can't hear you.
I think it's fine. Yeah.
Yeah. Okay. Good. Okay. Good. So I mean, just count the number, and then if you want to count the numbers, what happens with these slides here? Okay, good. So, well, I mean, this and that's the loss function. So we have somehow all ingredients that we need for our classification problem. Right? We define a class of functions. That's what we need, and then we have the loss function here, and then we say, well, why not? We have a training data, right? Training data is xi, yi, I from 1 to n. and this here is our average. It's empirical, the empirical expectation here of the loss function, and we want to minimize over a function class f, and want to find the best function that outputs us that minimizes some of the number of misclassifications. Right? So far, so good. However, and that's the point here, this is numerically infeasible. Right? I mean, it makes very much sense from looking at it as from a data science point of view, because you say, well, I mean, why not counting this number of misclassifications and find the function that does the job best? But if you want to give this function to our optimizer, or I mean, the optimizer would not be happy. It's very hard, in particular if you have large training data, to find the best function here. So what we do next here is we need a trade-off, and this happens very often in machine learning. That that the idea is it's actually rather clear, and this is the way you want to go. But then you come to the computational limits of your computer, and to the problem of, right, damn, we need some other idea here because we get stuck. And this is where we are at that point.
Okay, so Martin, there are some questions in the chat regarding the f of x.
Mm-hmm.
So I think some students have confusion. F of x is actually a continuous value. It is not like 1 or minus 1. That is the labels which which are the label data or the y's, So f of x could be and is normally a continuous value.
Was that the question?
Yeah, this was the question. I'm just explaining it myself, because there are like a lot of students asking this question. So maybe if you can go to the previous slide and briefly just also tell them, yeah, this is f. The f function is from RP to R, right?
Yes, f is from RP to R, and for now there is no constraint on that f. Right? It can be anything that is suitable, and we can choose function classes where, right? I mean, it's a question of how I want to design this algorithm, how good I want to be in designing this function class f. And why not talking about that? I can choose a function class really well. For example, I can choose f being consisting only of one function. Why not? Right? It's a very academic example. It's just one function, and the minimization process is trivial because I only have one function of choice, and I can plug that in. Right? And this is of course not. I have no room of saying how good the function could be. Of course, there are affine functions that always are a good choice, because very often they are good enough for the problem at hand. They do a good job, and from a numerical way, they are quite easy to handle. Right? So numerical, so linear functions play a main role in this data analysis part. But if you have a lot of data and you see that your affine function is not working, there is another class of functions that does a good job, and these are, for example, feed-forward neural networks. So feed-forward neural networks are also a class of functions that go from RP and that iterate on a certain level, and they will somehow match to the output layer R. I'm already talking about layers. I want to do that in the next, let's say in one of the following lectures. I think in 3 weeks or 4 weeks we'll do that. Right? But you can also go for quadratic functions and so on and so forth. One question was, if we set f equal to 0 constantly, that will do a good job, right?
No, I think this was not the question. The question was that why is 0 included in the 0 part, like that is greater than or equal to 0.
Well, you have to you will have to decide that. It's an academic question because it does not occur in practice. But you could also exclude 0 from the definition here.
Yeah.
define a loss function only on positives or on negatives, and you could exclude it. I think that does not make any harm. By the way, I mean, I like these discussions a lot, right? I mean, they give me the feeling of interacting with you, and that's not too bad.
Okay, so maybe maybe we just skip break and take this question answer session, right? We can do that.
Should we go to a break? I mean, it would be good to have a 5 minutes break here, because what we do in the next part of the lecture is seeing that how can we deal with this numerical infeasibility at that point, right? So let's have a 5 minutes break and see how we can consolidate these sets. Are only designed on convex sets, and convex sets are sets in some RP. Convex sets in some RP, and the idea is that if you have 2 points in that set, regardless of whether 2 points in that set can be connected with one line within that set. That's the idea. So 2 points here, and then they can all be connected here in that set, right, regardless of how they look like. So you would have here, this, for example, would be a convex set. My drawing is not so good, but this is a convex set here, okay? Because regardless of what the points are that I choose, the line that combines, that connects these 2 points is entirely contained in that set. This here is probably not, or is not a convex set, because this point here and this point here, if I want to connect with the line will lie outside of this set. Okay, so here also an example of a non-convex set. Okay, and formally you say a set is convex if x1 and x2 in this set C in RP implies that the line that connects these 2 points, so this is the line T x2 plus 1 minus T times x1, is also included in that set for all T in 0 and 1. Okay, that is the definition. And a convex function, another idea of a convex function is that if you have, let's draw it. Function f of x, and x. So if you somehow look at this function along this line that is always in the set, right? I mean, the line that connects these 2 points is always in the set. And if I start at this point x1 and I go to that point x2, and I always look at my function, say what is this function doing, and then I'm drawing that. That looks that should look in a way such that whenever I look at my measuring, whenever I look at the thing that measures my functions at that point and at that point, and I do a linear interpolation of these 2 points, then the real values of the function are always below that. So this is this is it. So that means that if or in formulas we say that this function f from C to R is convex if so this interpolation T times f of x2 plus 1 minus T times f of x1 is always greater or equal to f of, and now we, along this line, tx2 plus 1 minus tx1, right, for all t in 0 and 1, right, and all x1, x2 in C. Okay, so if we have that, so and one example is, for example, the function f from r plus to r. Sorry. No, f from r plus to r, and we say x is mapped to 1 over x. And this function looks like this. And this is a convex function. The function f from r excluding 0 to r, and x is mapped to 1 over x, is not convex. Right? Because the set it's defined on, where I look at it, it's not a convex set. And so it's always important to see on what set the function is defined. And yeah, so these kind of functions, they play a major role. Another example, this one example. Another example is f from rp to r, and x is mapped to any kind of norm of x. Why not? Squared. Also convex, and so on and so forth. And you can show that if f and g are two convex functions, then you can construct a function h that is the maximum of these two functions. It's a convex function. The sum of two convex functions again is a convex function. And if I have a non-increasing function g, and I concatenate that with a convex function f, then the outcome h, or the function, so then the concatenation of g and f is also a non-decreasing, is also a convex function. Right, so you can, I mean, this is important, because if you see a function, you can always see, you can answer the question whether this function h is convex or not convex. You can answer that very quickly in practice. For example, if it's the sum of two convex functions, or it has the other forms here. Yeah, but I mean, as I said, this is not the main part of this lecture, so have a look at it, and we just summarize it. For us, it is important to see what the benefit is in terms of optimization, and the theorem that helps us here is that a convex function f has a minimum. If a convex function f has a minimum, then it coincides with the global minimum, and it is unique if it exists. I'm just seeing here that I talk about strictly convex functions. So yeah, well, strictly convex here means that should I do that or not? strictly convex function means here that that we have the t of f x2 plus 1 minus t f x1 is always greater than f of t x2 plus 1 minus t x1 for t in the open interval 0 and 1. Right, so you have an equality sign only at the edge cases of your line, and in between you have this greater sign here. So that is strictly convex. And if a function is strictly convex, right, I mean that means whenever I have like these 2 points here in between, the real function values are always lower than the values that I got through linear interpolation of these 2 points. And if we have this, well, we can see, or I mean, one can show, we don't show it here, but one can show that if there is a local minimum, for example here, there is a local minimum of that function, it's also a global minimum, and there is only one if it exists. The example that you should have in mind here is this example 1 over x, because it's not so trivial to draw with this. Good. So is this 1 over x, because it's although it is a convex function, it does not have a local minimum or a global minimum. Right? So 1 over x does not have a minimum on R plus. Okay, so that's what you should keep in mind. Good. That means if we can replace our function for this the 0, 1 loss with a appropriate convex functions, then with an appropriate convex function, then we are happy, because then it's enough to search for a local minimum, and then the local minimum would automatically be a global minimum if we find it. That's the idea. So let's go to some yes or no questions, and let's see how that works. So let's use the poll here in this chat, and the first question is right or correct or not correct. Every convex function has a minimum. Yes or no? Okay.
that is quite uniform distribution. Okay, no, not uniform. Now it's getting split.
No, it's getting we go to a winner, and the winner is
no.
The winner is no so far. Let's see. I mean, we have over 90 participants.
Yes, guys, kindly use the poll options, not the chat option.
Yeah, exactly. The poll option, please, because the chat option is.
Yes, we cannot count it.
We cannot count it.
I mean, we can, but it's not efficient.
Okay, good. So 28 people.
Yuan said he doesn't have the poll option. Actually, you have the poll option. Everybody has the poll option. If you go to the participants, if you click on the participant list, then you can see there's like yes, no, this bar.
The green and the red button. Can you see it?
I don't see it.
Juan does not see it.
Now I see. Okay.
Okay, good. Yeah. So we have 11 said that every convex function has a minimum, and 33 that said that it does not have a minimum. And the answer is no, right? No. Right. So that's the correct thing, because not every convex function has a minimum. Right? I mean, in order to answer that question, we have to find a convex function without a minimum, and this function is, as I said, f of x is 1 over x, and f of r plus 2r, right? Nice convex function, even strongly convex, but without any minimum. Okay, that's a good example. Okay, the next thing is a function on a convex set. So a function on a convex set is convex if it has a unique global minimum. Is that correct or not? So think about it. A function on a convex set is convex if it has a unique global minimum.
So there is a question in the chat, but strictly convex function has a minimum, right?
No, because f of x is also strictly convex.
So Jianjan, did you get the answer? Okay, please say yes in the chat if you got it. Okay, so we have a tie on this question.
A function on a convex set is convex if it has a unique global minimum. Now, perhaps, I mean, you should get familiar with these kind of questions, because the exam is will also have multiple choice questions. And a function on a convex set is convex if it has a unique global minimum. That means, I mean, this question means, is it correct that by having any function on a convex set with a unique, by having any function on a convex set with a unique global minimum, does then automatically follow that this function is a convex function? This is how you should read that question. Right? A function on a convex set is convex if it has a unique global minimum. And the answer is no, it's not. Right? Example or counter example. Counter example is, for example, something like this. Comes here. Right? This is a good example. Right? It's defined on R. Defined on R. R is a convex set, perfect. And it has only one. There's only one global and unique. Only one, then it's of course unique. Only one global minimum, but it's not convex, right? Because if I go from here to there, I see that the function values are above the linear interpolation. Okay, so also no in that case, right? Okay, so read carefully these kind of questions. Either, if questions are correct, then you should have a kind of proof in your head why that should be correct. You don't have to write it down because we're not mathematicians, but you should say, okay, so is it correct? If yes, why? And if not, try to construct an easy counterexample. And this here is an easy counterexample. And the next question, or the last question here is, so I have to, a differentiable convex function has its unique global minimum at the point where its derivative vanishes? Yes or no? Why are you laughing, Umer? Okay. So if the function is differentiable, then it has a derivative at all points. And if we find a point where the derivative is 0, so where the derivative vanishes, is that also the unique global minimum here? Oh, I see. Okay, 18, 19 people. Think about it. Some time, yes, no. There's also a tie here.
Yes, it's
So
almost a tie here. So Lishan, kindly choose the yes or no option in the participant list, please.
So already 2 times no, so I say yes. That's good.
That's good, Daniel.
Okay.
So Yishi, kindly go to the participant and vote there. No, I regret. No, Lishan is saying. Okay. So 21, 25, 26.
21, 26.
20, 26.
Okay, good. Now, I would like to hear a few of you saying no. What were your ideas behind? I don't know whether we can do that here. Is that possible?
I mean,
Probably
maybe
not.
if you can raise your hands if you want to, then I can try to unmute.
But perhaps this is not the format of doing that. Perhaps I don't know.
Yes.
Okay, so okay, so a differential convex function has its unique global minimum at the point where its derivative vanishes. Yes or no? So I mean, I would say yes. Okay, I would say yes, and I would like to try to convince you or give a short sketch of a proof how that could work. So yes, right? So here we are at that point. Why? Why is that so? Well, if f has a local minimum, then okay, then it's derivative. Sorry, I would probably need a little bit more space. I have not thought about that so much. Let me erase it here.
Martin, I would say please don't erase because students really like your handwriting and they want these annotated slides.
Are you sure?
Yes, I am sure because they specifically asked for it.
Okay.
So please undo and create a new slide.
I don't know how I could do that now. Maybe next time. It was not so important what was written there. Okay. So why is that the case? So a differentiable convex function has its unique global minimum at the point where its derivative vanishes. And I would say yes. And why is that the case? Well, because you have the derivative f of x is 0. That means you have a local extreme point. Right, local extrema. Okay, and then so this is because f is differentiable, and then you say, well, local extrema can only be local minima because f is convex. So you can choose the convexity, saying that a local extreme point can only be a local minima, right? I mean, because f is convex, right? Because if you look at, it can either be this, or it can locally, or it can look like this locally, or it can look like this locally, and the only way that you don't have a contradiction to convexity is having a local minimum here. Okay, and then we can use this theorem. So then, if it's a local minima, then it's also the global one. Global minimum. Okay, that's some of the sketch, and that makes these differentiable convex functions so important in optimization, because all you need to do is you need to find the position where the gradient of this function vanishes and where the derivative is 0, and then you have 1. And this is actually, I mean, one of the main reasons why differentiable convex optimization is considered to be easy. Right? I mean, it's not easy. There are lots of books outside for convex optimization, but it's a topic that has been, where you have good results, and it can be considered easy if you have, from a data science point of view, if you have achieved this setting.
Okay, so Martin, maybe we take 4 minutes break.
Yes, if you want.
Yeah.
4 minutes break and gather the questions. Good.
So Martin, a student actually raised an interesting point here. I mean, it's I guess we can clarify that you mentioned like at the point where its derivative vanishes. So from this word, they probably, like, one student maybe got the idea that it means that the derivative sort of goes to 0, not like exactly equal to 0, and so like it goes to 0, so to say. So as in that case, this 1 over x function also can be treated in that scenario, but we actually meant equals 0 exactly.
Yeah. So where its derivative vanishes means where df of x is 0.
Mm.
So that means df of x is 0. Yeah. I mean, the reason, I mean, in an exam, I would state it more formally, probably the question here, so that it does not allow multiple interpretation. Other questions?
So there is one other question actually from Jim, and some other guys also sort of seem to have the same question. It's about the constant function. So we mentioned that we were talking about the unique global minimum, unique, and they were like sort of some students have a question that why not take the constant function as an example for no.
Yeah, well, I mean, that's correct. A constant function is convex, but not strictly convex, right?
Yeah.
And it has 0 everywhere, and the minimal value is the same, but the minimum is probably not the same. So actually here, this is actually a good point.
No, I guess we mentioned unique global minimum, so it already satisfies. I mean, it's already included in our statement. Like, we only want one unique minimum, not a whole list of points.
Okay.
Maximum is impossible on a convex function. Paul says, I don't understand what that means. Why do you think maximum is impossible on a convex function?
Well, the maximum on a convex function is possible.
It's impossible. Right? This is what Paul thinks.
Yes, but it's impossible on a differentiable position. If it's right, I mean, you can have things like you can have things like definition here on a compact convex set. And say, right, I mean, this function here, it has a local minimum, which is also the global minimum here, right? And it has a global maximum, which is the guy here, because it's defined on the edge. But it's not differentiable on the edge. I mean, these are the edge cases. Right? If you would have looked at the open set here, then it would not have a maximum. Right? Okay, good. So I think, I mean, all the questions point in the direction that you have understood the concept of convexity good enough, right? For now, that's perfect. That's fine. I mean, I have understood the yes/no balance in the answer Q3, because there might be a minimum and minimal value, confusion about that for the constant function. I should have said, in order to make it like more concise, I should have added here the differentiable strictly convex function. That would have made it a little bit clearer, probably. So next time.
Okay, so Jeff, I would add a little bit on that. Still, there seems to be some students who are confused about the global minimum, unique global minimum. So when we say unique global minimum, it's not a value, it's a point, right? Yeah. So we are talking about a point, not a value. I mean, the value could be unique, but we are not interested in that in the value. We are interested in the point. At which point does it achieve? Is that point unique or not?
Yes. And then I add here strictly. And then we are fine.
Yes.
But that's good. I mean, thanks for the discussion. I mean, that was I think, a good discussion. It always takes some time, but I think it's valuable at some point. Here, I think it's valuable enough for now concerning the convexity task. Let's go back to logistic regression, okay? And let's have a look at our function that we have here. So we said that we are minimizing the empirically expected 0,1 loss for the training samples, and we ended up here in this function. We've already seen it, and we've seen that this is numerically infeasible. Now, if we now replace the 0,1 loss that we have here, I mean, I have drawn it here. If we use that 0,1 loss by another function or by other functions that are convex and that imitate as good as possible this 0,1 loss, we arrive at a feasible and very good binary classification problem, actually. And there are many of these convex, they're called convex surrogates or convex replacements of the 0,1 functions. And there is, for example, the hinge loss, log loss, or modified Huber loss. I don't want to get into the detail of how the formulas look like, but just to want to give you that the idea that replacing this 0,1 loss here with some convex functions that imitates what the 0,1 loss is doing will give you very good classification methods, right? And also very feasible classification methods. So that's the idea. And one way of looking at logistic regression is that there is a particular loss, named the so-called log loss, that does the job in replacing the 0,1 loss with as a convex function. So what we do is we replace the 0,1 loss by convex surrogates. For binary classification, we choose an appropriate function class. For example, the affine functions. That's always a good choice if there is nothing else. So it's always a good point to start with, and then to see how good your classification algorithm actually works. And if you do that, then your optimizer will output the best decision function very quickly, right? And this is the idea. So the rough idea of this binary classification task. Your optimizer can digest it very easily, and there are good optimizers. And there are whole books on convex optimization and researchers that have looked into that topic of this convex optimization. So for the logistic regression part, we have the so-called log loss here that will take the replacement, right? Replaces the 0,1 loss here. Okay, and it's the logarithm of 1 plus e to the minus z. It falls a little bit from the sky here, but the advantage is that you see how it is somehow related to Huber loss and to other losses. And if we choose our function class to be affine functions, like this here, like the affine function classes, then we end up in an optimization problem. Hold on. That looks like this. So we find our optimal function, our optimal weights, V and W, by minimizing the optimization problem. Sum over I, and we just plug this minus yi here into this function and see that it works. I mean, actually there is missing, but it doesn't matter. There is here the normalization factor missing for the number of training samples that we have. Okay, so this is the cost function that we have, and this is the function that we can now feed into our optimization problem, and it will output us the optimal values W and B that will define our affine decision function. There is no closed form solution to that optimization problem, but it's convex and it's differentiable, and it can so be reassigned to the problem to our optimizer of choice. Okay, so we have this. So I mean, let's go one step back. So we looked at this data problem. We had the 0,1 loss because we thought, well, it's a good idea to count the number of misclassifications. If we say, well, the number of misclassifications leads us to a function where we say, well, it's not convex, and optimizing that is infeasible. We have replaced it, and we say, okay, so replace the 0,1 loss with this log loss leads to a function that should do the same job in some sense, or a similar job. And then we arrived at this problem where we can say, okay, so now optimization is not a hurdle anymore, right? We have a convex problem. And now a next step, and it depends on what you want to do and where you want to go. A next step would then be, well, do I solve this optimization problem, or do I give that to someone else? And very often in machine learning, you have good publications where you then have a concrete cost function, you really dig into the problem, and you go for a kind of gradient descent method or a Newton method, or what kind of optimization methods there are, and see how they really how they really look like for this particular problem, right? And then you can choose the very nature of this problem to design even better and optimization problems. Right. So, and this is, I mean, if you are interested in how that looks like, it's in the lecture notes. There's a paragraph on that, how gradient methods could look like for that optimization problem. And I thought that we have more time, but time is already over. And there's another approach, namely a probabilistic approach to logistic regression, where you arrive at the same cost function, but where you have a more statistical interpretation of things that are going on. And I would like to offer you both approaches, right? I mean, this was more from an optimization point of view, the 0-1 loss replaced by a convex surrogate, which was the log loss. And there is another approach that motivates the logistic regression that helps us interpret the results in a statistical way too. What should I do? And should I start with that now for the next 5 minutes? Or are there enough questions so far that we can discuss? Umer?
We have 5 minutes left, and we don't have any questions regarding the
That's
lecture.
Good. Yeah. That's good. Then I trigger it so that it makes it a little bit more motivating for you to come back next time. So let's look at an example. So let's go for a probabilistic approach to logistic regression. We should arrive at the same cost function and should arrive at the same parameters at the end, W and B. And let's look at an example. So assume that we want to predict the probability of death due to COVID-19 infection patients, given some parameters. Right. While reading that, I already see that it's not well stated, the problem, because the probability of death is 1 for all of us. The probability of death of COVID-19 patients, I don't know, within the next 14 days from the data acquisition, right? For example, like that. Right? If we say, well, this is our problem, we have some, and given some parameters, we have our input parameters x, right? So this here is our input x. Okay, and here perhaps you see a little bit what I mean with designing a random variable, because here we have, like, for example, oxygen saturation, the temperature of each individual, whether he or she has fever or not. You can look at coughing frequency. So how often is the patient coughing within the last 1 hour or so? The age should play a role. It should be a role whether it's a smoker or non-smoker, and all these things. Okay, and the more you know about your patients, the better you could design this input variable x. Right? If you would be just a data scientist and you would go for a big end-to-end machine learning part, you would, I don't know, probably measure everything you can, including videos about the patient and the behavior. You would end up with a very, very, very large input vector x, and hope to get enough information for predicting the output y. Okay? But this here is obviously an expert that is designing this input variable x. And we have an output variable. Why is that gone? Something did not work well. Did not work well with the update of my slides. I have to recheck that. Okay, so this is the input x, and the output of our classification of our problem is output. Let's say, well, we had typically up to now we had y, and we model it with -1 and 1. But for this approach, we will go for I call it z. Due to other reasons, z is 0 to 1, saying that z is 0 if z is 1 if death occurs, and 0 not, right, if the patient survived. This is our output variable. And we assume, and what we assume here is the assumption that we have is that the probability of Z is in some way related to a linear combination of our input parameters. Linear combination of the input parameters. So, right, I mean, the probability of Z, so let's call it small p, and we have here the p on the one side, and we say the probability here is probability of death, probability that Z is equal to 1. This is how I should name it. Probability of Z is 1 is related to a linear combination of the input parameters. So this P is, right, somehow the W transpose times X and input. And this, okay, so time is over here. Now this here is of course something that is not, I mean, that is not between 0 and 1. Probabilities have to lie between 0 and 1, otherwise it doesn't make any sense. So the idea is how to squeeze this real number into a number between 0 and 1. And to that end, we have this, we have this log function here, sigma, and I'll talk about that next time. Right, this function here, sigma of t is 1 over 1 plus e to the minus t, and it takes any real number and squeezes it into a probability between 0 and 1. Yeah, so yeah, so this is what we will see next time. I mean, how we can predict or how we can design that logistic regression with statistical motivation, and ending up to the next function, and also see how we can interpret it, a result in terms of probability, namely whether we are correct or not, which will also, and this is the nice thing, which will also answer the question: what happens if the set is 1, is 0, right? In this edge case that we discussed, right? And then we see why this edge case is not interesting in practice. Okay, so this is where we have to stop here, unfortunately, and hope to see you again next week. Thanks a lot.
Thanks.
Have a nice week. Enjoy your time and stay healthy. Tschüss, bis bald.
Bye.
Bye.